normal distribution from the mean. So then you add those numbers up and divide by 213 to get probability of landing of getting 8, 10, 12, 14, or which the score would be 1, 10, 15.
And I drew those lines up there inside the table. You see that to show those are the ones we want to think about that are within one standard deviation from the mean. So now the next question is like, why would I have asked you about that? And those who maybe know a little bit about the normal distribution know that that's what we're trying to remind you of, make you think of here. We have an example in our warm-up of a symmetric unimodal distribution. Bell-shaped, as someone said. So we'll talk about the normal distribution.
It came from your water bottle.
Sometimes people like to call it the bell curve too. All right, so the normal distribution, sorry. We're going to say a few things about the normal distribution today, and keep in mind your quiz tomorrow is on homework 1 only. Okay, so not the stuff we talked about yesterday, but today, all the stuff from homework 1, which is lots, right? There's 50 grams, class data, all the stuff you learned back in the day, median, mode, quartiles, percentiles, deciles, 70 counts, box and whisk counts, modified box plots, outliers, all this stuff is on the quiz. Yeah. Maybe not. Yeah, maybe less than 1. Okay. All right. So, hopefully you're feeling good about the early part of this unit, classifying data, all that kind of stuff. Okay. Let's discuss the normal distribution. Again, also some of the people call it the bell curve. Also, you've maybe heard it called the Gaussian distribution, named for Carl Friedrich. So it looks like this. And our data from the warm-up looks something like that too, maybe. This is our first example, and our only example in this course, of a probability density function. Continuous probability distribution, right, where that values here to take on any real number in some range. The actual support of the normal distribution is actually negative to positive infinity. You guys get the note sheet there? Yeah. Okay, I just want to make sure Francis looks at these. Really bad. Okay, you got it. All this is word for word on the note sheet, I think. So. Yeah. You can annotate instead of noting. You can annotate. So yeah, just to be clear, technically the support of the normal distribution is negative to positive infinity. All reals is like the domain of this function. And so almost nothing in the real world is like really normally distributed, but things are so closely approximated by normal distributions so often and approach this distribution in the limit that we're flexible with it. But we already said some of these words today. Symmetric, and then single peaked we also mentioned. Distributions that are symmetric don't have to be single peaked, but this one is. And by single peaked we also could say unimodal, if you like. And we should mention too that the mean and the standard deviation completely specify a normal distribution. If you tell me what the mean and standard deviation of your, if you tell me it's normally distributed, then I know exactly what distribution you're talking about.
So for example, your fancy cutout for Messer, would that not be single peak because it had 2?
Yeah, it might not quite qualify. It was roughly normal. I don't know. We'd have to test for it in the way we did in the warm-up today, maybe. And we'll say more about that in a second. We use this kind of notation earlier when we were talking about binomial sometimes too. It's not a notation we'll use a lot, but you may see it out in the world, and so you just know that this means that the random variable x has a normal distribution, and I'm telling you the only two things you need to know, the mean and the standard deviation, because like I said, that's completely specified what normal distribution you're speaking about. There's one particular normal distribution that we care about, the standard normal distribution, which has for its mean 0 and its standard deviation 1. And so that's the one we'll be working with most. But certainly true, all of these, with any mean and standard deviation, you get other ones as well. You don't have to know this. I wrote this on your paper, though, because I thought, you know, this is the kind of thing that I need to tell you, because your stat teachers won't tell you this. The actual function rule for this function that you'll use every day in AB stat is this rule right here. You don't need to know it, maybe you memorize it, but it seems like a little bit of a crime. I just have to throw a little shade, stat teachers, right, a little bit, because like really, you're going to use a function every single day of the year, and you're not going to tell people what the function rule is. I mean, in what sense is this math rather than magic, you know? By the way, if you ever need this rule, it's painted above the lockers up here on the wall.
Field trip.
Field trip, like up 2 feet. Look, there you go. You can see it on your way out and be like, what up? Normal distribution. Standard normal distribution. So
But I
anyway,
say, what up, Mr. Chase?
you can do that too. Yeah, I think it's important maybe to say one more thing about probability density functions. This is, like I think I told you early on when we were doing probability functions back in last unit. I told you my favorite name for the probability distributions we did, and all of the ones we did were discrete probability distributions. I called them probability mass functions. And if you're a physics person, then maybe you understand this analogy. Mass, finite point masses versus density. This is a density curve. So mass and density make us think about physics a little bit, right? And when we add up density inside this curve, we get a mass of some kind. Okay, whatever. The point is, the areas represent probability still. The area under this curve is still, the whole thing is what? Should be what? 1 or 100%, or however you want to say that. Right? So the other thing that's a little bit of an anathema is that in a stat class that you're actually finding the area. We're going to be calculating areas under this curve, and at no time are you speaking about calculus. So we are going to use like a little bit of a black box here to help us today, literally black or perhaps gray or red box, to calculate the values that represent areas under this curve. But when you get to calculus, let yourself be reminded that you have thought about area under the curve before, and that's a thing. Yeah. So every day, really, in stat class, you're using a function that no one told you the rule of, and you're doing calculus, and no one is telling you. They're just saying, do it on the calculator. Area under the curve, just do it. So, all right. So there, I think I'll get off my soapbox now. I'm down. Okay. One other thing about the difference between a probability mass function for a discrete probability distribution and a probability density function for a continuous random variable is that if you plug in a value to the probability mass function, what you get is the probability. If you plug in a value into that function like last unit, what you get is the probability of that value occurring, right? Not true for a probability density function. If you plug a number into this curve, the value you get is not the probability of that value. Okay? The thing that's meaningful here is summing areas under this curve. So we'll say more about that as we go forward, but just a caution that that's not what they work a little differently. Okay. If you change mu and sigma, I think the expected things happen that you would guess happen, right? And I have this picture there for you. You can see that changing mu amounts to a translation of some kind. Changing sigma amounts to a some kind of dilation. In all cases, though, whether you're the red, the blue, the green, the purple, you have an area underneath of you of 1. Okay. By the way, feel free to graph this on your calculator by plugging in that, by going to y1 and typing in that function there, right? You can see what the normal distribution looks like, y1, right? It's also remarkable that there's like a pi and an e showing up in that formula. Beautiful, right? It's wonderful. Just should pique your curiosity and even more underlying thoughts about math. Okay. Of course, one of the main reasons we are thinking about the normal distribution is that it is useful and is somewhat ubiquitous. It comes up in lots of different situations, certainly test scores of various kinds, but actually maybe more naturally in these kinds of things, right? Many things in nature. We don't want to be under the impression that everything, there is this kind of, this error in thinking that one could approach here. That like every continuous distribution that I'll ever run into is always a normal distribution. That would be going a little too far. But it is very common in nature to see normal distributions. But there are lots of other wonderful and useful and prevalent continuous probability distributions that are useful for modeling things in the real world. You can go look up the exponential distribution, or the gamma distribution, or the beta distribution, or the chi-squared distribution, or the Pareto distribution, Cauchy distribution. They're like all sorts of beautiful and useful distributions. So that's important. It comes up when you have lots of these kinds of things. And then actually, the most important thing about it, we can't even say much about in this course. We'll save it for AP Stat. And that's called the central limit theorem. It turns out that, in fact, actually, this is in some ways a way of thinking about, even before you see data, expecting maybe that something will be normal. And the way to think about that maybe is to think, if you have something that's the sum of a whole bunch of independent random processes, then you get something normal, the sum or the average, regardless of what the underlying distributions are. If you have a sum of what's effectively an infinite number of independent processes, like, I don't know, like might be your lifetime, things you ate, things you, your genetics, all these different, the sum of all these different things, if it's the sum of lots of different factors that are all independent probabilities, then you get something normal. And that's a really loose and not very good way of talking about this, something called the central limit theorem. Turns out that when you take lots of samples from lots of this identical distributions, independent distributions, and sum them or average them, you always get a normal distribution. So I'll say no more about that. But I'll just say that it's like there's this. It's also kind of a very, very central idea in a stat course. But for our purposes, we'll just kind of look at the data. Yeah, I'm not going to ask you to predict before you see data. What do you think? Do you think this is going to be normal? It's hard to say. I think it's an intuition you have to really work hard to develop, I think. I'm not sure I have it either. But we can look at the data afterward. If you show me some data and maybe think about whether it's normal, like you did on the warm-up today. And that's what we were kind of doing, right? We saw, in fact, that this was almost roughly, not perfectly, but roughly happening on the warm-up. That within one standard deviation of the mean, we were getting about 68% of the data. And that's expected for a normal distribution. Any normal distribution should have these kinds of observations. 95.4% of observations falling within 2 standard deviations. And within 3, 99.7% of observations. And so by the time you've gone a distance of 3 standard deviations away from the mean on a normal distribution, you've caught almost all the data. If you're on a normal distribution, if you have some characteristic we're measuring that we think is normally distributed, and you're like 3 standard deviations above the mean, say you're 4, like you practically don't exist, or you're really weird. You're very, very weird. 5 standard deviations, I think you're probably lying, right? This is what I think is happening, whatever. So we have it's really, in some sense, we can use these standard deviations as kind of a measure of weirdness, right? How weird you are. Well, let's actually try a problem now. You have this in your notes, I think, right? Thinking about the head circumferences of men in the army. Okay, how about that? We're saying that it's approximately normal. Someone has to come and tell you that, first of all. And we've been given, as promised, the mean and the standard deviation. And we said that's all we'll need. And so we can use this picture, where mu in our picture will be 22.8. And then each of these will be a new value, which is the standard deviation plus the mean, or minus the mean this many times, right? Now I've given you some very convenient values here to help you first get into this. Why is 21.7 a really convenient value today? It just so happens to be exactly 1 standard deviation below the mean, right? And 23.9 inches is exactly 1 standard deviation above the mean. So it's very convenient of us to do that. So maybe we can just immediately write down the answer. What is it? Wonderful. So 68% of those, so that's just kind of, were you awake on the last slide? Okay, what about B? This is a fair question. I have a head circumference of 25. I would like to be able to say that I'm better than a certain percentage of people. Wouldn't I? I'd like to lord that over them. I don't know, having a big head, is that good? I'd like to have a big head about having a big head. Where is that? Is that a convenient value too? It is. Where is that? It's exactly located at 2 standard deviations. So I'm asking, I guess if I'm asking for the percentile, I'm asking for what percentage of this curve lies to the left of the line I just drew. Right? How are you figuring it out right now, people who are thinking about it? There are a couple good ways, that's what I'm asking. What way are you thinking of doing it?
Like 50 plus,
Yeah, if you're going to add up all of these, you might do start with by saying 50% because it's symmetric, and then add those two. I like that. Give me another way you're thinking of doing it, someone else. Is that a hand, Brent? Oh, yeah, so you're saying it should be 95.4%. Except that's the percentage of data that lies within 2 standard deviations of the mean. So that counts all the area we want except for over here, right? Right? Isn't that just this part? In between negative and positive 2 standard deviations. Yeah, so the other way you could do this is by using the complement, right? I mean, since the whole area of the curve is 1, you could subtract these two. Regardless of what you do, hopefully we agree. I don't know. What do you get? What'd you get? 97.7? Now, there must be, something's going on here, because what's going on here? Is that, what did you get if you did over here? 97.8. Maybe there's some rounding issues happening, right? So we'll have to be a little careful about that. In fact, before the class ends today, you'll have ways of calculating these with much more precision if you'd like, and we could actually maybe settle this debate. Did you have a question, Fawn, or that was it? You mentioned the rounding. And down here, I guess we could say 2.2, but again, maybe we have some issues with rounding. Yeah. Yeah. So as you can see, even on this slide, don't you see? Aren't we measuring already like a sense of weirdness? Before we ever even calculate the probability that your head was 25 inches in circumference, right? Before we ever said what percentile you're in, we already actually knew that you were really weird, right? Just because we said you are 2 standard deviations above the mean. Like, I didn't even need to hear too much more. I was like, okay, that's unbelievably large head. Wow, wow, good, excellent job with your head. And there's nothing special about 2 standard deviations. It's certainly true that if you have a head size of 24 inches, 24.7 inches, that you should be able to ask about how weird you are too, right? Almost as weird as this person. How many standard deviations would that be if you were at like, if your head was 24.7 instead of 25 inches? How would you calculate that? How many standard deviations is that? I might start by calculating this distance. What would that be from 24.7? Let's do, I'm just making this up, but 24.7 inches, say, right? So how far away is that? First, maybe calculate from the mean. I don't even care what the answer is, but what are you doing? Doing this minus this, yeah? And then what? And then divide by 1.1, right? To be able to say out loud how many like standard deviations that is, yeah. Why is what linear? Oh, it's just really like a measure of units, right? It's like how far away are you in, like say we wanted to measure in like miles, how far this is from here, right? You could totally do that. What would you do? You calculate this distance by subtracting, and then you divide by, or you multiply by whatever appropriate unit conversion is, right? So that's all we're doing. We're just like asking how many standard deviations it is, right? It's kind of a unit conversion almost. Okay, well keep in mind what you just said. Took the value, subtracted the mean, and then divided by the standard deviation, right? So by the number of standard deviations that you are away from the mean, that phrase we've just been giving, we have a name for that. It's called a z-score. And this is a formula not that you should memorize per se. It's one you know, don't you? Because you just said it. It's in your heart already. It's just a unit conversion, right? Find the distance you are away from the mean, and then turn it into standard deviations. Yeah.
So would you ever say, would standard deviation there be a decimal?
Absolutely, yeah. So on that last example, I picked one that would come out to be 1, right?
Yeah,
Exactly.
1.9 standard deviation. You ever round it?
I mean, one could, yeah, absolutely, but it's perfectly fine is what we're now giving permission for. It's perfectly fine to say 1.9 standard deviation. It's a wonderful thing to say. I love saying that. Well, I know, let's not get carried away, but you know. Could this ever be negative? The answer is yes, when? Yeah, when the value of x is something less than the value of the mean, right? We get something negative. And so just be careful about that. In some sense you might be thinking, well, that's like a bug. Well, that's actually a feature maybe, right? Because when it comes out to be a negative number, we know that our value is, yeah, we don't just know the magnitude of the weirdness, we know the direction of the weirdness, right? Right? We know that if you're 2 standard deviations above the mean, you're weird. But it also tells us if you're like at a z-score of -2, that you're weird in that direction, right? You're weird by having a smaller head than like almost everyone or something.
I prefer eccentric.
Eccentric is great too, yes. Sorry if I'm throwing around pejorative terms. Okay. Let's talk about how weird these 3 songs are by measuring their z-scores. Go ahead. I think this is on there, right? You have this in front of you? I'll call on 3 people in a second to give us some z-scores. Consistent, straightforward calculation.
So would x be the minutes? Oh, they gave us everything. This is simple.
All right, Anya for the first one. Agreed?
Yes.
Speak up if anyone says something wrong. Holly? What about B? Negative 0.627. And Zach T? What about C? The weirdest song of all. Okay. Really, the power comes not by just doing that there on those problems. Good job, though. Well done. But in comparing 2 distributions, right? Like, for example, say you took an ACT and an SAT. If you knew the mean and standard deviation, and you could assume perhaps that they were normally distributed, maybe you could say which one you did better on, right? Relative to other people is maybe how you have to say it. Because of course you can't, in some sense, you can't possibly say in an absolute way which one you did better on. Like, it means nothing. Of course you did better on the SAT. You got like thousands of points higher than the ACT, right? Good job, right? But that's not what we really mean. We mean like what percentile did you get, or what, we don't even need to go there. What z-score did you get? How weird were you? I'm sure all of you would have positive z-scores in that particular situation. All of you are above the mean. Yes, you are. All right, so here we've got a test for neuroticism. This is a test you maybe don't want to score high on. And there are 3 different tests for this. Which one did you score the highest relative score on? Notice you don't even have to have probabilities to answer this question.
Not like a bigger number I can score on this.
Yeah, I think a bigger number is higher, exactly. You don't. We're asking which one did you get the highest relative score on?
So if you still
I mean,
just-
which one did you? I mean, that's not desirable, right?
Wait,
Yeah,
so
yeah,
are you
yeah.
still
So it's
doing
the one
this
far
experiment?
from here.
The one that's the highest. It's actually got the greatest value. So I'll just give it to the first person who has it. Who has the three values for us? Katie, go.
Negative 1.17, negative 1.2, and negative 1.5.
To be fair, by the way, negative z-scores are what you want on this test. Okay. There are obviously other people who got positive z-scores, but you are the kind of person who is below average on all of them, so that's good. That's at least good. This is the kind of thing, like I said, that you don't want to, as high achieving as you all are, you don't want to achieve high on. But it looks like the first one, yes, is the one that we score highest on. The one you might want, though, is the last one that scored. Yes, exactly.
So, for example, those score of 36 on the first one, it's like 1.17 standard deviation below the mean.
Right.
Oh.
Yeah. So, going back to even Francis's question, if we're at a standard deviation of exactly 2 above, we even went on with the head circumference problem. Then say what probabilities were associated with that, right? How much probability lay to your left? Left lie to your left.
I have
Right?
a thing on my phone with all the tenses.
Thank you. I would need to borrow that for sure. So, but it's fair to ask, what percentile are you if you have a head circumference of 24.7 inches? That's not a nice, if it's like 1.9 or 1.8 standard deviation, you'd like to associate to that a probability. Or we'll say a p-value probability associated with a particular z-score. So the way we can do that is with the calculator feature, and again, this is the black box that I was promising you. Keep in mind that it's actually us calculating area under the curve. We're doing calculus. What? But just trust the calculator, I guess we'll have to say. I don't know.
That's why it's
We're
called
forgiven.
calculus.
Normal CDF, good name for this. Go to the same place you found binom CDF. The syntax is a little different here, though. The syntax can either take 2 arguments or 4 arguments. If you give it 2 arguments only, it will assume that your mean and standard deviation are from a standard normal distribution, that is 0 and 1. So we'll calculate a couple of these together here.
So it's lower, like negative 1.00.
Yeah, so you're always doing low, high. So this is a little different than, this is nice of them to give you kind of boundaries here. So for this first one, we'll actually type in normal CDF and then negative 1, 1. And before we even press enter on our calculator, what should this come out to?
0.6.
Yeah, it should come out to about 68%, right?
Wait, why don't we have to plug in the standard deviation? Like,
If it's a z-score, then we're talking about a standard normal distribution where we have mu equals 0 and sigma equals 1. If you want to type this in and then later also try typing it in comma 0, comma 1, you'll get the same answer.
wait, why did I get 0.6?
Yeah, you'll get 68 point, what? What do we say?
What did I do?
68.26 something percent. Okay, whatever you say.
Oh, second distribution.
And not a huge shocker there. What should you get for this one, even without normal CDF? What's the probability that a z-score is greater than 0? Should be 0.5, yeah. But how do you enter that? Since normal CDF calls for a left and then right bound, I think I know what greater than 0. I think I know the left bound is 0, but what's the right bound? A really big number. We already made a great point of saying that, like, hey, by the time you get to like 4 standard deviations, there's just like no one out there. There's just nothing there. It's a desert. So if you put like 10, you're probably fine. Try doing this a couple times. Do normal CDF 0, 10. Try normal CDF 0, 100, and see that really it doesn't matter. And if you put like a whole bunch of zeros, like you're super, super, super safe. Like really, 1 0 is probably enough. Okay. Yeah. So try some of these other ones here as well, and we'll get some answers. Thinking about what we just said there too, you may need to use like a really big number in the place of infinity. Yeah.
So is it 0.5 or 0.5%?
You can say, sorry, I was inconsistent. You can say one or the other. Anything correct is fine. You can say 1 over 2. 1 over 2 if you like. Yeah. Yeah, what does this one even mean down here? Can someone help us interpret that? Well, the absolute value of z less than 1.32 would mean like from negative to positive 1.32, right? That we have a distance away from 0 at 1.32. But this is greater than, so what does that mean? It means we are looking for z-scores that differ from the mean by 1.32 or more. The absolute value of 1.32 is absolute value, but it is 1.32. Yeah, so we're saying that. So we're saying if your z-score, like what things qualify for this inequality? How about a z-score like 1.7? Wouldn't that work? If z is 1.7? Yeah. If z is negative 1.7, won't that work too? If z is 17 or negative 17, also that's fine. If z is 0.6 or negative 0.6, not okay, right? So you see where we're in here. In fact, for each one of these, it might be good to shade a little normal distribution, huh? Negative 1, 1. Or for this one down here on F, so maybe also draw a picture for these. So we got this two tails there, out there. So calculate all those. Let me quickly say, we can come back to give the answers there, but that's not the most interesting part. Computation is never the most interesting part. Okay. I would also like to be able, so you can do a couple homework questions. We got to go in a minute. There's also a calculate feature called INVNOR.
Sorry, interruption, Richard Montgomery High School for these weather-related cancellations. Today's varsity baseball game at Watkins Mill has been rescheduled for tomorrow. There will be no JV or varsity baseball practice today. Today's away tennis match at Wooten has been rescheduled for Friday. JV softball practice is also canceled. And now SGA President to let us know who are class winners from today's elections.
Good afternoon, Richard Montgomery. Thank you to all the candidates who ran for this SGA election. Here are the results. For sophomore class officers, our next sophomore president is Claire Guido. Our next sophomore vice president is Nick Asante. Our next sophomore secretary is Danielle Carter. Our next sophomore treasurer is David Smith. Next on to junior class officers. Our next junior president is Kushtav Sami. Our next junior vice president is Alambia Katagianakis. Our next junior secretary is Jonathan Wardman. And our next junior treasurer is Lawrence Reeder. For senior class officer, our next senior president is Nyreen Johnson. Our next senior vice president is Sydney Waincoat. Our next senior secretary is Michaela Estwick. And our next senior treasurer is Mackenzie Fay. And now for school-wide class officers. Our next school-wide vice president is Adrian Andreessen. Our next school-wide secretary is Maureen Zufat. Our next school-wide secretary is Maureen Zufat. Our next school-wide treasurer is Jeffrey Tran. And then our next school-wide president is Raina Choi. Congratulations to those who were elected, and a special thanks to everyone who ran. Here's a wonderful next year. Cheers.
Yeah, this is homework. Yeah. Numbers are all a fiction.